Good evening, guys. Hope you're doing fine. Okay, so welcome to this evening's class. So we started the journey on organic chemistry, all right? Because one of the key areas and one of the areas in which JAM bring out most of their questions, organic chemistry. So we started last week with introduction part, talking about uniqueness of carbon, uh, explanation on carbon, why carbon was chosen as the element that revolves around organic chemistry, the chemistry of carbon and compounds containing carbon. And that means we're talking of covalent bonds between compounds because any compound involving carbon is a covalent compound. All right, so we explained the uniqueness of carbon, hybridization, uniqueness, catenation, the ability of carbon to form straight chain compounds or ring chain compounds. All right, and then it's some variable oxidation states, which makes it easy for you to hybridize. So, I want to go in depth into that this evening. I want to go in depth into that. All right. So, bonding in organic compounds. Bonding in organic compounds. All right. Now, atomic orbitals on carbon. A carbon atom does not form ions easily since it has 4 valence electrons. I told us last week the electronic configuration of carbon. For the traditional method, we have 1s2, 2s2, 2p2. Now the ground state of carbon configuration is 1s2, 2s1, 2px1, 2py1, and 2pz1. All right. Why? I think yes. That's the excited state of carbon. The ground state is the normal configuration 1s2, 2s2, and 2p2. While the excited state is 1s2, 2s1, 2p1x, 2p1y, and 2p1z, showing the x, y, and z in the 3-dimensional plane, representing them in the 3D plane. We're going to see that as we go on now. Now, it satisfies the octet rule. We know what octet rule means. We know all elements involved in chemical reactions or chemical bonding have one mission. And what's the mission? To get to the octet state or to get to the duplet state. So, carbon satisfies the octet rule in compounds by sharing electrons, which is a key property of covalent bond or covalent bonding. One of the key properties of covalent bonding is that electrons are shared. Electrons are shared. All right, electrons are shared between the two participating atoms. Why? For dative bonding or coordinate covalent bonding, one of the elements is responsible for sharing so that both elements can get to octet state. Now, we'll see the expression of the configuration and we see 1s2, all right, we'll see the energy level going up, all right, 2s2, then 2p1, 2p which ought to occupy 6 electrons, 2 pairs each, we see 1 1. Now, relating that to the p orbitals and the s orbital, look at it, and I told us last week that the s orbital is spherical in shape. Now, the second thing to note is that these are the orbitals that exist on atomic carbon. These are the orbitals that exist on atomic carbon. These orbitals, they are the ground state configuration of carbon. All right, 1s2, 2s2, 2p2. All right, and don't forget, according to Onsru makes us understand that if we want to, we can represent some electrons in terms of spin, equal and opposite spin. But before we do that, according to Bauer's principle, we are going to fill all the pairs, all the slots singly before pairing will occur. And that's the same principle applicable here. That's why we didn't put the 2 electrons in the first circle of 2p. We put them one by one. Once we are done with the first 3, completing the first 3 circles with individual spins, then we can now place the opposite spins to each of them so that they can become paired. All right. Now, all right, so we now move on to hybrid orbitals. Now, we say when carbon atoms form bonds with each other, we describe the resulting bonds using hybrid orbitals. That means the bond formed between carbon and some compounds, because of the uniqueness of carbon and because carbon is one of the key elements that undergo hybridization, we say that the bonds formed can be expressed using hybrid orbitals, which are formed by mixing. I told us hybrid means new orbitals formed from existing ones. All right. So these hybrid orbitals are formed by mixing the carbon's atomic orbitals. When carbon atoms bond to 4 other atoms, the 2s orbital and all the three 2p orbitals in the valence shell combine to produce 4 sp3 hybrid orbitals. Take for example the case of let's say look at the example below. So you have 1s orbital, look at it, you have 2s and 2p. Okay, now when it undergoes bond, look at it, you now have sp3. What happens is that the s bonds with the p. Don't forget, in the ground state of carbon electronic configuration, you have 1s2, which is standing for the first orbital there, which is the 2s. 1s2. Our main focus is not even on the 1s orbital. Our main focus is on the 2s and 2p, because they are the orbitals that combine to form the new orbitals, to form the hybrid orbitals. Now, 1s2, we don't have issue with that. Then you come to 2s2, 2s orbital, and 2p2. Can you see? So I said, when carbon atoms bond to 4 other atoms, the 2s orbital and all the 3 2p orbitals in the valence shell combine to form 4 sp3 hybrid orbitals. What do I mean? So when carbon reacts, it goes from ground state to excited state, and the configuration now changes. Instead of you having 2s2, you now have 2s1. So it's not easy for the 2s orbital to bond to the 2p orbital. So you have 2s1, then you have 2p1 in the x direction, 2p1 in the y direction, 2p1 in the z direction or z direction. Initially you have what? 2s2, 2p2. All right, 2p2, just now 2p2 in the x and y direction. But now you're having 2s1, that's 1, 2p1 x direction, 2p1 y direction, 2p1 z direction, making 4. You now have 4 sp3. You now have 3p orbitals. 2p1x in the x direction, 2p1y in the y direction, 2p1z in the z direction. So you have 3 of those p's plus the s. That becomes sp3. We now have 4 new orbitals from. Initially we had just 3. Now we have 4 orbitals. Now hybrid orbitals, look at this again. I said the last statement, all 4 sp3 orbitals are at the same energy level with 1 electron in each orbital. All 4 sp3 orbitals. That means the new orbitals formed, or the hybrid orbitals formed, they are all at the same energy level with 1 electron in each hybrid orbital. Look at it now. You now have 2s1. Is that not 1 electron? 2p1 in the x direction, one electron. 2p1 in the y direction, 1 electron. 2p1 the z direction, 1 electron. Can you see? So they are all at the same energy level with 1 electron in each hybrid orbital.